design.
And how did you verify that? This is a theoretical finding, or it's a practical finding?
It's an implemented, and it's the result of implementations on actual hardware. So for the Vivado HLS, in the tool you can set the constraint, like this is the clock period constraint that I want to achieve, and then in the tool we try to do the design for you. So it could meet the constraint only at 20 nanoseconds. So it was only at this particular clock constraint that it could generate a workable design for you. Whereas in the proposed flow, this is the results that I'm showing you for the proposed flow are without actually setting up any constraint, because normally when you constrain your design, you can improve the timing performance, but this is without constraint. So without constraint also it's faster. So the synthesis tool at the end will report what is the maximum clock period that you can attain.
I think the main problem is still the
significant. What was the design that you did?
Sorry?
What was the design? Do you think you said that you didn't do? Did you actually design something real?
So in this case, I implemented the 53 tap FIF filter.
Okay. And sorry, I didn't see that.
Yeah.
So seeing it's going to go 3 or 4 core functions that your tool is optimized for.
Yeah.
Why 53 tabs?
Okay, why 53 tabs? Good question. Because the device that I'm using here in this case, it has only 32 DSP blocks. So the point was to demonstrate that if you follow the methodology and if you have more number of multiplication operations compared to the resources on the chip, then how do you go about distributing those operations on those resources?
Was 53 like just the first number you pulled out, or did you try like 54, 55, 57, 52 and pick one to get the best numbers?
Okay, I tried 53, 40, some randomly chosen numbers which were bigger than the limit on the device, and for each of them you had it better. It's just that I'm showing you like this. Okay, and then, so one other thing that I looked at was the system level constraint. So in your application, you can have a data initiation interval constraint, which basically means how often you are going to feed a new set of inputs to your design. Now, if you see figure 1, which is a large data flow graph, as an example, and if you try to resource share operations in this one, so the typical data path for area minimization would result in figure 2. Now, if you look at figure 2, you have 100 addition operations shared on one adder. Now, if this is your design, it will work, but it will not meet any initiation interval constraint that is less than 100 clock cycles, because it will not be available for processing until it finishes all those 100 operations. So we decided to have a look at this constraint and use it as a measure to partition the data flow graph into different segments, and then dissociate within each of those segments, and finally stitch those partitions in time.
This is automated?
Yeah.
So where does the DFG come from? Do you do that by hand, or is that just like...
No, the DFG comes from... Okay, the DFG comes from... There are different benchmarks. So some benchmarks give you the DFGs, like you have the UCSB Express benchmark. Then we also made use of LLVM compiler framework, so it gives you the intermediate representation of your application, which is a data flow graph. So we read that graph and then we partition.
For your particular like 53 length filter and your 4540 matrix multiplication, where do those DFGs come from?
Same from the C code.
So you had a C code, which is like an NR filter, and you compiled that, and you extracted the FT from the compiler. Got it.
Okay. So, so what did we achieve by doing this analysis and by taking this constraint into consideration? Now, if you take this constraint into consideration and you have a large number of partitions in your design, you can order those partitions in terms of the benefit that they bring to error reduction when you resource share, and then you can choose the most profitable partitions and stitch those partitions in time while you leave the rest of the design as it is. So as a result of which you can get multiple design points, all of which satisfy your constraint and give you different area and clock points to consider, so that at the end the designer can choose which one he wants to actually implement. Now if you vary the II constraint, you can also get more design points. These are some of the publications from my PhD work. But other than my publications for my PhD related work, I have also written for industrial design magazines. So these are all of those, because I like to communicate my ideas as well as share and learn from other people. So where is the future for high-level synthesis? So far we have focused mostly on auto-generated RTL, but an auto-generated RTL should also pass the design rule checks. And if you look at existing ways of generating this RTL at the end, sometimes you will find that it will fail the physical design rule checks that the physical synthesis tool will use, which means that when you are doing your hardware binding and your HLS flow and you're generating your RTL, there's something wrong. So that is one area. Then the readability of these auto-generated RTL is terrible. Now why is this important? This is important if you want to look at code coverage and code linting, and if you use the existing, the way currently it's done, you will have a lot of problems you can run into problems in ensuring that the code coverage is proper and the code linting takes place properly. Then you have the low power design methodology aware HLS. So if you are looking at low power based designs, you can express your power intent using UPF and CPF standards. So how can an HLS methodology leverage upon those intent defining standards or ways and use it to generate a design that has multiple voltage islands or multiple voltage based modules in a design? And the last one is physical synthesis aware HLS, which is basically looking at an HLS flow that is aware of how physical synthesis is actually done. Now by physical synthesis, I mean steps like mapping, placement and routing, because if you can abstract that kind of information also earlier in a design, you can probably improve the way binding and other operations are done in HLS. And the last one is inclusion of domain-specific knowledge in HLS methodology. So what do I mean by domain-specific knowledge? If you look at hardware design, I'll give just one very small example. If you look at multiplication, there are a number of ways in which multiplication or multiplier architectures can be done in hardware. Now, in an HLS methodology, you have the multiplication operations, and on the other hand, you have the circuit designers who come up with different kinds of architectures for these kind of operations. So how do you abstract these to this kind of information and bring it here so that someone who is using an HLS methodology doesn't have to learn these things, but your methodology itself takes care of this kind of information and gives you results accordingly. So that was the part on my PhD related work and other aspects of high-level synthesis. Now I'll talk about system resiliency.
So can I ask so it's a high level, it's a very broad area, right?
Yeah.
So if I was to ask you, what's your forte, and what of that do you bring to your thinking on system resiliency?
Okay.
What would you say is something that you are really good at, and you can go back to your industrial experience, to what you did for your PhD, and you also seem to you wrote for the industry magazines. There must be something you're really passionate about